Now I could literally read my mind. 1 second. 1 second. B, C, I. A couple of weeks ago, this was just an idea I was trying to execute. But today, I was finally able to create it. Yes, it's kind of reading my mind to type what I want. Essentially, I just created this virtual scrollable keyboard with letters across the screen and this selector that moves right or left across the screen towards the letters that I want to choose. And then, whenever I want to select this letter, I just blink. This movement of the selector is actually controlled by my brain, by basically thinking about it. It isn't just another cool gimmick that anybody would use, so how is it significant? What did it have? And who might actually use it? Prominently, such an application of brain-computer interfaces would help two kinds of people. First, people with physical limitations like people with motor disabilities or repetitive strain injuries, and it could help them replace the physical keyboard with their thought. Another example is people with speech limitations. For example, Stephen Hawking, rather than twitching his cheek muscles to choose a word, he could just think about it. This process is interesting, but wait. So how can this thing just read my mind and send my thoughts to the program? How does this system work? Basically, this is just a simpler version of a motor imagery BCI that reads the brain signals whenever somebody is thinking about moving, whatever kind of movement, but in my case, it's more about moving right or left. When this happens, the brain fires some electrical signals from certain parts inside of it, like the primary and sensory motor cortex. Then, the sensors or electrodes on the Muse Headband actually detect those signals. Okay, but how will the signals actually reach the virtual keyboard on my computer? There has been multiple methods that would facilitate this process. Prominently, BlueMuse and the MuseLSL packages would help me do that. The BlueMuse software utilizes the MuseLSL Python package in order to help me connect the Muse Headband to my computer and transfer the data. And essentially, the MuseLSL package would do the work behind the scenes to transfer this data. But wait, because different parts of the brain attenuate those signals as they reach the electrodes on the Muse Headband, it isn't actually easy to detect them. Thus, a simple code that would detect right or left movement isn't really enough. Here comes the power of machine learning, where it will be able to detect the patterns in the brain signals that I first record, and based on them, it will be able to detect any other brain signals it receives. So how did I create this machine learning model? The first step was data acquisition, where I used the BlueMuse and MuseLSL packages that would allow me to directly stream the EEG data from my Muse Headband to the computer. After I collected the data, I imported it into the widely used Edge Impulse platform to help me create a TensorFlow machine learning model for my program. I configured the import settings, adjusted the parameters, created the machine learning model, generated its features, then trained and tested the machine learning model, and eventually I took this machine learning model and exported it from the Edge Impulse platform onto my code as a TensorFlow machine learning model, and I implemented code that would interpret the EEG data streamed from the Muse Headband to the computer in real time, and then it will translate it into corresponding commands. If you want to learn more about the technical details of this project, just check the link in the description down below to an article I wrote about all of the technical details and the steps that you need to follow to create such a project. I'll remind you about this at the end of the video. Continue watching. I got a satisfactory accuracy. However, to be honest, it could be better by importing more data to the machine learning model and giving it more of a training time. However, it was honestly a diminishing return for me because it got really good at this stage, and any further improvement would just take way more time and without a real tangible benefit. And this is how it turned out. As you can see, I'm deeply thinking of moving right or left, and then when I blink, it writes the letter on the console. But actually, the process wasn't all flowers and roses. I actually faced a lot of problems with collecting the data from the Muse Headband to the computer, because the first project I followed and kind of got inspiration from did it kind of wrong and in a complicated way. However, I actually reached out to that person who created that project, and he gave me his advice, and that was actually what led me to using the BlueMuse and MuseLSL packages. Thanks, Thomas. Researchers are currently involved in the research of the motor imagery BCI domain, and it is really promising since it would help countless people in this world. But right now, they actually have some limitations. Like, for example, different brains have different varying brain signals, and the current machine learning models won't be applicable for all people. Finally, the BCI space is a really interesting and fast-growing field, with companies like Neurable and Neuralink creating breakthroughs that might shape the future society along with other technologies. Thank you, and stay tuned for other updates. If you're interested, don't forget to read my in-depth article about this project linked down in the description. Thank you. Salam.